And following that short note, I'm going to start the recording, and we're going to get started. You guys can feel free to put your hands down. I already got a head count for who was here for last time's class, so we're good. Lena says I can't join the gym kit. I'm outside. Okay, that's all right, Lena. Maybe if you really want to play, you can step inside, but that's all right. No worries. Okay. I'm going to go ahead and get started. Today it's going to be a sort of follow-up, but also an addition onto class we had last time. Oh, great, we're putting up bomb emojis. Goodness, Jeff. Okay. Today's topic will be we're still focused on finding life on exoplanets. And
Hi,
we're still
Lauren.
using hi Daniel, it's good to see you. We're still focused on analytical chemistry. Today we'll be talking about a specific technique that analytical chemists use, and I should probably put in the name of the technique. And the technique we will be discussing is emission spectra. Spectra is plural for the word spectrum, which is like relates to the rainbow. Okay. Before we get started, has anyone heard of an emission spectrum? This is definitely an advanced high school topic, but because we have quite a lot of people in here, I wonder if any of you guys have heard of it. And it's okay if you guys haven't. Okay, okay. Lena messaged me and she said sort of, kind of. Okay. That's okay. You guys are still very young. Emission spectrum is a very advanced topic, really. I didn't learn about this until my sophomore year of high school. So you guys are very much ahead of your time. Okay. For some reason, the little gallery is blocking my thing and I can't see. Okay, much better. All right. Ethan, I just saw that you joined. You don't have to. Okay, I think there's another Jeff here. You didn't really miss anything, Ethan. We're just getting started. We have two Jeffs in this meeting. What the heck? Jeff, is that the same Jeff?
No.
Oh, wow. Okay. Wow. What a coincidence. Okay. All right, so let's get started and talk about the basics of emission spectrum and how these things are formed. Okay, so everyone knows that atoms like to be stable, right? If atoms aren't stable, they're not happy. And for atoms to be stable, the electrons in the atom are arranged or they are placed in certain levels. And when an atom is stable, we say that the atom is in its ground state. If the electrons are in, if the electrons have absorbed energy and they're in very high levels, that electron is no longer in its ground state. It's not stable anymore. When they do, when these atoms do absorb energy, the energy actually transfers to the electrons in that atom, and they can do the electrons, they're able to jump to higher energy levels. Think about rings around an atom. Electrons start at the very base, and when they absorb energy, they are able to jump to higher rings. And we call that an excited state. So when an atom is stable, we say that it is in its ground state. And when an atom is excited, the electrons are therefore excited. And we say that that atom is in an excited state. One thing you guys one thing that would be interesting for you guys to remember is that there are normally two electrons in like the lowest ring or lowest sublevel, and then from there on it goes 8, so 2 8. And if you don't see this kind of 2 8 pattern, then you'll know that one of the electrons has absorbed energy and it has jumped to a higher sublevel. However, because when atoms are excited, they're not stable, these electrons want to come back down. Does that make sense? These electrons, they don't want to be holding all this energy. It's uncomfortable for them. It's like playing hot potato. You don't really want to hold the hot potato for too long, right? You kind of just want to throw it to your friend, get rid of it. That's what these
Hello.
electrons are kind of doing. They don't really want to hold on to that energy. Hi, Colby. Um, you didn't really miss anything, Colby. I just got started. But when these electrons, they release this energy because they want to be stable again, these electrons return to their original levels. And the atom becomes stable when this happens. However, these atoms, when these electrons give off this energy to return to their ground state, I mean, it becomes apparent that the atom is giving off energy, right, guys? Does that make sense? Uh-oh. Does that make sense, guys? I hope that makes sense.
What are we talking about?
Okay. We're talking about emission spectrum. I'm going over the very basics of how atoms absorb energy. So Colby, when an atom absorbs energy, that energy is given to the electrons, and the electrons jump to higher levels. However, when they jump to higher levels, they have a lot of energy, and so the atom is unstable. So the atom wants to return to this kind of ground state or stable configuration. And so the electrons will release that energy and return to a lower ground state. So they'll basically come back to their original levels. However, when they release this absorbed energy, obviously the atom gives off energy. And I was just asking your fellow students if that made sense. I hope that makes sense. Is that okay, Colby?
Yeah, makes sense. What?
Okay, cool. Makes sense. Great. I will come back to this photo later. This photo shouldn't really be on okay, you know what? Actually, I'll talk about the photo right now. So when these atoms give off energy, they give off a form of electromagnetic radiation. And there are a lot of forms of electromagnetic radiation. The first kind of form that we know is visible light. So the colors that we see, your blue, your red, your green, your primary colors, blah, 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 blue, yellow, blue, red. Like anything that you can see that is visible light. It comes from, like light bouncing off certain objects and going into your eyes and your brain processing it. However, there are other kinds of electromagnetic radiation. There is infrared. Have you guys heard of infrared?
Yeah.
Okay, yes, there's infrared radiation. There is X-ray, there is gamma, there is ultraviolet, and usually we're not able to see these other kinds of radiation, right? You can't see X-rays, you can't see infrared light. If you guys have infrared sensors at home, you guys know that you can't really see the beam of electromagnetic radiation that infrared and X-ray gives off. However, we can see visible light. And so when these atoms give off, oh my goodness, Colby, I loved that filter that you had on for a second there. When these atoms give off energy, they're actually giving off electromagnetic radiation. And there appears to be something in the chat. Okay, Jesus, Ethan, relax. And this electromagnetic radiation, it can turn into many forms. It can turn into X-ray, gamma, infrared, and it will also turn into visible light. And so what happens is when these atoms give off this energy, we can see that some of the electromagnetic radiation that they give off is actually given off in visible light. So we can see that these elements like helium, neon, argon, krypton, xenon, they give off a certain color when we impart those atoms of the element with energy. So what we're doing here actually is, for example, helium. What we're doing is we're taking there's something in the chat. Okay. Ethan, try not to flood the chat if you don't have a question. What we're doing is we basically have a certain container of helium. Helium has two protons. It is a noble gas. It doesn't really like to interact with other elements. But what happens is when we take a coil and we run electricity through helium, the helium atoms absorb that energy they jump to higher levels, and then when they return, the electrons return to lower sublevels, they give off that absorbed energy, and that absorbed energy takes the form of electromagnetic radiation, and then it turns into visible light. And we can see that helium turns into this sort of pinkish purple color, and neon is this sort of orange light, and argon is this sort of darker purple. You guys have seen like neon lights before, right? Think the Vegas Strip, think like 80s retro style futuristic, like the mash between retro and future. That you guys have seen neon lights before? Okay, let me show you guys what I'm talking about. Yeah, okay, perfect. Uh-oh, that's the wrong screen. Let me share my Chrome. Okay. Think about like these guys. If you look at if you look at like something like this, okay, this is not necessarily neon gas in here, but a lot of neon lights are based on this kind of idea that if we run electricity through one of these noble gases, they'll glow. And so it's pretty cool. We don't really do this anymore. I think it's kind of become a thing of the past. We kind of just rely on LEDs now, but I think it's cool to know. Okay, any questions about this slide, guys? The next slide will also talk a lot about how this kind of radiation works. No questions? No questions? Great. Okay. Oh, Colby, yes.
It's just kind of confusing, that's all.
Okay. Yeah, I understand it's a
I have a
difficult
question.
Yes, Daniel.
Why do the coils get different colors?
You will see in just a second why the coils get different colors, okay? Okay. Okay, Colby, what are you confused about? Okay, Colby.
Like, or like, you like see the color. It's a thing.
How do you see the color?
Yeah.
Right, okay. So energy can take many forms. Energy can be in the form of X-rays, in the form of gamma radiation. We're getting into kind of complicated stuff, but if you think about, okay, so Einstein dealt a lot with this. He believed that light is made up of a bunch of different particles, a lot of different waves. Actually, no, I won't get into that. That's definitely a little bit too difficult for you guys to handle. Colby, can you re-ask your question so I can better answer it?
Like, how do you see the colors of like different like those things down there?
Okay, so why do the colors happen, right?
Yeah.
Right. Okay. So what is happening is we are giving energy to the atoms in helium. And what happens is the atoms in helium, they absorb that energy. Simply because they do. They're greedy, I guess. And so the electrons absorb that energy and they jump to higher levels. I talked about that earlier. But when they come back down, they release this form of energy called electromagnetic radiation. And this can be all sorts of different kinds of radiation. This can be X-ray, this can be gamma, this could be infrared. However, in this specific case, we can only see the visible light. We can't really see if it's giving off X-ray radiation. We can't see if it's giving off infrared or gamma. And so what comes back to us is simply what we can see. We can only see the visible light that it gives off, only wavelengths inside like the visible light spectrum, because we can't really see gamma. We can't see X-ray. If you've ever gotten an X-ray, you don't see like X-ray beams going to your body.
That would have been scary.
Yeah, yeah, that would have been a little traumatizing for younger me.
Wait,
Yeah.
Lawrence, I have a
Yes,
question.
Daniel. Yes.
So, you know lightning?
Yes, I do know lightning.
Like, is it actually real? Like in cartoons that, like it when it like shocks you, like you can see the bones or something.
Um, I think yeah, okay. I know what you're talking about. Like in cartoons, if someone gets zapped, like their bones flicker in and out of the image, right? Is that what you're talking about?
Yeah.
Yeah, no, that definitely doesn't happen, Daniel.
Okay.
Yeah. That's just like cartoons. I mean, if you watch Tom and Jerry, like Tom gets hit by a train and he's fine. So, I mean, yeah, it's not based on reality. It is a fun show though. And so it has a lot of good animation techniques as well. Okay. Colby, did I answer your question?
Yeah.
Okay, great. I'm gonna move on to the next slide. Oh, appears to be something in the chat. Right, it's not like your flesh disappears, right, Colby? All right. Let's talk about how we go from electromagnetic radiation and visible light to the emission spectrum. Okay, so if you guys look at this first band right here, this is the emission spectrum of it appears to be hydrogen. The little H here signifies hydrogen. How do we go from the visible light, like just the pink glow? How do we go from the pink glow to these bands of light on this black strip? And so that's what we're going to talk about now. There appears to be something in the chat once more. What is NM? Okay. Colby asked a great question. NM is nanometers. Nanometers, this measures the wavelength of the light. Wavelength is like think about how concentrated the light is. If you have really high wavelengths of light, it's really, really dangerous. Think gamma. That can destroy your DNA. It can cause cancer. It is very, very dangerous. Why is iron on the last strip? I really don't know how they get the emission spectrum for iron. That will be something I'll have to look into. That's actually a great question. Sarah, what's up? Sarah? Sarah, you have your hand raised. Okay. Okay. I think there's something in the chat. How many nanometers are in a meter? Is that what you're asking, Colby? I believe 10 to the ninth. That's a billion.
Then, oh, okay.
Yeah.
No.
1 billion nanometers in a meter, I believe. How many nanometers are in a meter? Yep, that's a billion. Yep. That's a lot of nanometers. Can you repeat what you said? Yes, I'm happy to. So we're looking at this kind of what we saw earlier, we saw this. And this is just kind of a tube that's glowing pink. And so the question then becomes, how do we get this pink tube to something where we can see the individual kind of like bands? You see how if I zoom in really close, that's not supposed to happen. If I zoom in close, you see this blue band, this other blue band, this light blue band, and this red band. So how do we go from this giant like pink glowing thing to the emission spectrum? This thing is the emission spectrum. And so I was merely saying that I'm going to talk about that now, but I got some questions. This kind of nanometer, what you asked about, Colby, is a great question. So did I hear something? Okay. So Colby, nanometer basically measures how long or what the distance is between each wavelength of light. And that may sound really difficult, but just think about it's a measurement of how concentrated the light is, or really how dangerous it is. Yes, Colby.
That's really small. Like, I don't think we could be able to see it.
What's up? Can you repeat that?
I don't think because nanometers are very small. I don't think we'll be able to see it.
Right. It depends what nanometer. Like if you look at like 486 nanometers, we can see that. That's light blue for us. That's the way our brain interprets 486 nanometers. Something like gamma is, I mean, I'm not really sure what the nanometer measure of gamma is, but it is very small. And that's why it can be really dangerous. Gamma will destroy the DNA in your body. It will pass right through your skin. It will blah blah blah. It will definitely kill you. Okay. Let's talk about, yeah, let's talk about how we get this emission spectrum. What happens is we have this bink, we have, sorry, bink, geez. We have this pink, like glowing tube. And what we do is we place a slit over the tube so that the light travels through the slit and it hits a prism. The prism, what the prism does is it diffracts the light. If you guys ever hold up like if you hold up a pair of glasses to the sun and you get the sun to shine through the glasses, and you can see that the glasses actually break up the sunlight into a rainbow. And so this is what the prism is doing. It's taking this pink light and it's breaking it up into the components of light that make up this pink. So if you mix this purple, this dark blue, this light blue, and this kind of orange shade together, you'll get that pink. And you guys can see how this band of purple corresponds to this band. This band of, darker blue corresponds to this band. This light blue is this light blue band, and this orange band is this last kind of reddish orange band right here. Is everyone okay with that? Basically, we're diffracting the light that is produced from the tube that we talked about earlier. Everyone good here? What is gamma again? Okay, great question, Jane. Gamma is a form of highly dangerous radiation. Let me see what the wavelength is. Give me a second here. Okay. Gamma typically falls between 0.0001 nanometers and 0.01 nanometers. So it is a highly concentrated beam of electromagnetic radiation. It is really high energy. It can damage the human body severely. I mean, it is dangerous, trust me. Is that okay, Jane? Uh-oh, my screen share is okay. Yeah, gamma is extremely small particles that are going really fast. Yes, Einstein thinks about electromagnetic radiation as particles moving in a wave, basically. And that's definitely too advanced for you guys, but it is kind of like small particles, yes. Okay, Jane said, yeah, great. Okay, I like how you have helium in your name. That's very funny since your last name is H-E. That is a joke that is not wasted on me, Jane. Very creative. Okay, this is our kind of visual, like the visible spectrum that we can see between around, I'd say 425 and 725 are the colors that we know. Remember that gamma rays have about 0.0001 nanometers, and these guys fall around 450 nanometers, like 725. And so that should put into perspective the difference between gamma rays and something that we can see, like visible spectrum. If you guys think about something that is even longer than this, then you're looking at radio waves, you're looking at your microwave, you're looking at forms of radiation that are not as dangerous, which is why we are around radio waves so much. My phone is giving off radio waves. My computer is, my desktop is, and so we're surrounded by radio waves, quite literally. Didn't Hulk become Hulk when he was trapped in a gamma bomb? Oh my God. Ethan said, yeah, but that's stupid. He should get cancer. Maybe something went different. Nothing went different. He should be dead. Oh my God. Okay. I'm really not sure what happened to Hulk. I do believe he underwent some kind of electromagnetic radiation treatment, but goodness knows if he was subject to gamma rays. I, if he was subject to gamma rays, he would probably get cancer. But it's a movie, so do we really care that much about reality in a movie? No, we don't. Okay. Ethan posed a great question earlier about how they find the electromagnetic spectrum, sorry, the emission spectrum for iron here, which is Fe. And honestly, I have no clue. I genuinely don't have any idea how they do that. And so I'm going to, while you guys play the Gim kit, I'm gonna figure that out. And I'll let you guys know after the Gim kit. Great question, Ethan. Amazing. I've never thought to ask that. They burned iron. I really don't know how they got this. That is fascinating to think about. I will look into it myself. Okay. Any questions on emission spectrum, boys and girls? Colby has 1 more minute. Sad. Okay. If there are no questions on emission spectrum, we're going to talk about how emission spectrum can help us find life on other planets. Okay, so we all know that there is something called an emission spectrum now, right? This is this band right here at the very bottom. And this is our hydrogen emission spectrum. However, there's something that is called an absorption spectrum. Can somebody look at this absorption spectrum and this emission spectrum and tell me what they see as the difference? Can anybody spot any differences between these two? Oh, okay. Colby has to go. I'll see you later, Colby.
Bye.
Bye-bye. Bye-bye. Okay. Does anybody is anybody able to spot differences between this first kind of band that I'm circling here and the second band, which is the emission spectrum? Does anyone want to take a shot at guessing? Okay. Okay, it's okay if you guys don't see anything. That's all right. I think, okay, so if you guys just, okay, wait, there's something in the chat. In the first one, the empty spaces are the color spaces. In the second one, yes, that's exactly what I wanted to hear, Ethan. Thank you. So Ethan pointed out a great point where if you guys look at the bands in the hydrogen emission spectrum, which we looked at earlier, which we already learned about, they're the bands that are missing in the absorption spectrum. And so if this is emission and this is absorption, then when something absorbs, okay, so okay, how about I explain it like this? If you layer the emission spectrum onto the absorption spectrum, you will get a complete rainbow, basically. You'll get the entire visible wavelength, all of visible light from deep purple all the way to your red, and then your darkest shades of red that near black. And so that's the difference between absorption and emission. What we can do with absorption spectrum is we can look at absorption spectrums within the context of astronomy, within the context of trying to find life. Does anyone remember what transiting planets are? We talked about this last class. Transiting planets, anyone? I'm going to give everyone a second to put something in the chat this time, because I know Ethan and others like to throw stuff in the chat. Anyone have any ideas on transiting planets? Does anyone remember what those were? Okay. People weren't here last class. That's all right. Okay. I will go over transiting planets quickly. What happens is when an exoplanet, which may possibly have life on it, and we're trying to determine if it has life, this exoplanet will pass in front of its star, and that is what we call a transit. it simply passes in front of its star. It's almost like an eclipse, except with an exoplanet. And it's not with our sun. We want to look at transiting planets because they possibly have life on them. And one of the things that we want to determine when we try to find life on exoplanets, we want to see what their atmosphere is made out of. If the atmosphere has oxygen, that's a pretty good sign, right? All life depends on oxygen. We breathe in oxygen, we eat plants that produce oxygen. The cows, the chicken, the different kinds of meat that we may possibly eat if you guys eat both, like if you guys are omnivores. Yes, even bacteria depend on oxygen. Yes. Some bacteria use like photosynthesis, I think, but I mean, trust me, all life depends on oxygen. And so when we look for signs of life, we want to look for oxygen. Great. Let's talk about why that's important within the context of chemistry. So when a transiting planet passes in front of its star, that starlight shines through the atmosphere of the planet and it reaches our eyes. It reaches Earth eventually. Okay. So when that starlight passes through the atmosphere of that planet, the atmosphere of the planet absorbs some of that energy of the starlight, and then it gives off an emission spectrum, really. And when that emission spectrum gets to us, it is turned into basically what is an absorption spectrum. So if hydrogen is present in the atmosphere of the planet, it will absorb this wavelength of light. It will absorb this dark blue, this dark purple, dark blue, light blue, and this kind of orangish red. And so when that starlight reaches us after transiting through the atmosphere of the planet, these certain wavelengths of light have been absorbed by the atmosphere of the planet, and they'll show up as just black bands on our absorption spectrum. And when we look at this absorption spectrum, we can realize that, hydrogen is present in the atmosphere of this planet, which, may be good, may be bad. But what we're really looking for is oxygen. And so when a gas absorbs these wavelengths of light, we can tell because the absorption spectrum that reaches us is missing the bands of light that are absorbed in the emission spectrum. Okay, any questions, anybody? Okay, great. If there are no questions, I'm going to stop my screen share. I cannot talk today. Oh my goodness. I'm not sure what's happening to me. We still have 3 minutes left in class. Okay, I'm gonna end the meeting a little bit early so that we can get to the gim kit. The meeting is ending in 3 minutes anyways. But if you guys want to stay for the gim kit, you guys are happy to rejoin. I'll figure out what you guys want to play for the gim kit later. But I'll see you guys back here in a couple seconds. I'm gonna stop the recording. It's gonna be put onto YouTube. Probably around 25 minutes after class. So if you guys want to go back and review anything, you guys are welcome to. Okay. Thanks, guys. Thanks a bunch. I'll see you guys all in a quick second.